Thank you so much. And I just want to especially thank the conference organizers for giving me a second slot to present. This is Imprint Energy's first time at this conference, and we're really appreciative to be able to broaden our reach and audience at this conference. So I'm really excited to talk to you about designing safe and thin batteries for high-volume IoT applications. Imprint makes ultra-thin printed, safe zinc batteries. And if you Google search printed batteries or flexible batteries, you'll probably see images generated by Imprint Energy. For a number of years, we have been showcasing to the world that batteries can have different shapes and sizes that have never existed before, and they can be made and put on surfaces that have never had power electronics before. And we're really passionate about providing a inherently safe battery chemistry, one that doesn't explode or shape change or leak. And we want to give designers the ultimate design freedom. Rather than having a battery that you have to design around, we love being a part of the early design discussions and enabling the products of your dreams. So this is all made possible by our battery chemistry called zinc poly. It's a sandwich of layers, of which each one of these layers can be printed. So they literally start off as an ink or a paint, and then we screen print them into whatever shape and size that we want. And the enabling material in that stack really is that orange layer. It's a solid electrolyte. So everything in this battery is solid state. There's nothing that leaks out or whatnot. And it gives us a lot of really exciting features. Besides the form factor, this is a rechargeable chemistry, and there are some performance benefits to this chemistry in particular. What I think is really delightful about the way we make these batteries is that we screen print them much in the way that t-shirt and art and electronics are printed. And so this is an age-old process method. It's very scalable and tuned for high-volume manufacturing. And so I like to say that our gigafactory already exists all over the world. A lot of print tools exist everywhere. It's ubiquitous. And we don't need to build out that capacity. So actually, we partner with manufacturers that have SMT lines, print lines, both sheet-based and roll-to-roll, to produce these batteries. And this is a roll of batteries that literally was printed on a roll-to-roll line, much like stickers and labels are printed. So pretty amazing. And you can see that it can scale very quickly in terms of volume in a very cost-effective way. So I want to talk a little bit about why we're here and how we even found this community, being a battery company. So at first, we were really attracted to the IoT space. There was a lot of pent-up demand for better batteries and a major, step change rather than an incremental update to existing batteries. And we were, from a core value standpoint, we really resonated with what this community wants to do. Bring better quality data so that we can make better decisions about our lives, about our processes, about the environment. And one element of that is just ensuring that we can put sensors and power sensors in places that haven't been reachable before. And we felt like our batteries could do that. When we dug into IoT hardware, what we realized is that these types of devices are actually quite simple. They're really only a handful of components. And battery oftentimes is a very key and enabling piece, which is a great place for a technology company like us to be in. In conventional, portable electronics like your phones or your watches, battery might occupy 25 or 30% of the volume, but in these IoT devices, they could occupy more than 50% or even 75% of the volume. So they're a really integral part to the design and the manufacturing of the IoT hardware. So when we first started the company, we thought, just like everybody else, we needed to maximize energy density in a given volume. And we knew we had an advantage here because our chemistry is much more inherently stable in ambient conditions. We just don't need the same level of hermetic packaging that is traditional for any other sort of battery chemistry. So we don't need metallized cans, we don't need metallized bags. And so even in just a volume, by replacing some of that packaging with active material, we were able to provide a higher energy density. But we thought that it was a little bit peculiar because there have been other battery companies that have come before Imprint, and many of them claim to have pretty reasonable energy densities. And so we thought it was strange that very few of these companies had any, if not little, traction in the IoT space. So we dug in a little bit deeper. We started to talk to customers, and also we started to test what our customers needed with respect to our batteries. And what we found out was that the IoT space in particular is very unique in that the demands on the batteries are quite harsh. Rather than very gently discharging and pulling a load onto the battery, this is a very pulsy sort of application space. Oftentimes your device might be asleep and then all of a sudden there needs to be a big surge of current. And those type of pulses are just really hard on batteries in general. And so to explain how that impact how that has an impact, if you look at the red curve above, that is the typical voltage of a battery that's being discharged continuously and gently, for example, like in a watch or a hearing aid. And where your device voltage limit is, that ends up dictating your runtime or your theoretical capacity. But what happens when you start pulsing the battery is that the battery's voltage drops, and that voltage drop is directly proportional to the magnitude of the pulse current as well as the internal resistance of the battery. So simple V equals IR. And as a result of that pulsing, oftentimes the battery's voltage hits that voltage limit much sooner, leaving you with much less practical capacity, much less runtime. And so with a lot of our customers, when they were testing other types of batteries, other competitor batteries, they were basically getting negligible runtime, and it was not meaningful for their products. So we thought this was really strange because the metric of success here is really internal resistance. But our customers really had little to no intuition about battery internal resistance. And now that I think about it, it makes a lot of sense. Oftentimes battery data sheets don't even list internal resistance as a metric on the list. And so, it's not something that we typically interact with or communicate. And so the intuition that smaller batteries just have higher internal resistance was just not intuitive to a lot of our customers. And so I wanted to go over this thought exercise just to really showcase how the impact of internal resistance becomes even greater for these IoT type batteries. So if you think about your smartphone, 1,000 milliamp hours, it's a lot of material that's stacked like an accordion into like a 3 millimeter pack. That's a battery that has about 100 milliohms of internal resistance. And so let's drop an order of magnitude to a smartwatch or a wearable. These batteries have, hundreds of milliamp hours in capacity. So an order of magnitude less in capacity, an order of magnitude less active material. But you can see that the internal resistance of these batteries increases by 3 orders of magnitude. So it's not a linear relationship, it's almost exponential to some degree. So going to IoT devices, where you need more compact batteries, where the capacity is another order of magnitude lower, the amount of active material that's actually in that battery is more order of magnitude lower. The impact here is that the internal resistance of these devices, these batteries are quite high, it can be hundreds of ohms. And so that's been a challenge because a lot of these batteries are just not suitable for giving proper runtime to these IoT products. And on top of that, it is difficult to communicate about internal resistance because you can't use one singular number to describe it. Internal resistance is actually a dynamic response to how the battery is loaded, what environment it's in, how old the battery is, or even how much it's already been utilized. So it's a really complex quantity, and it makes it really difficult to compare from chemistry to chemistry. So, amidst all that confusion, we realized we could simplify things for customers. And the way to really simplify this is that we realized the biggest link, the biggest impact to battery design and the internal resistance was really the actual radio itself. It is by far and single-handedly the most power-hungry component in any one of these devices. And so in pairing our battery solution with the radio, that helps simplify for developers and designers what choices are actually available, rather than having to boil the oceans and test every single battery. And so when we were looking at different IoT products, we looked at all the different sort of radios that customers were considering, and what we found was that LoRa was really interestingly situated. It was giving customers the data range that they were looking for in a cost-effective way, but at the same time offering that with very low power. And that low power, that low peak current has a direct impact on the maximum internal resistance that is necessary in order to power that radio. And so you could see there's an inverse relationship. So the higher the power requirement, the lower internal resistance the battery needs to be. And so what we found was that a lot of competitor batteries that have come before us, they just didn't have the low enough internal resistance for chemistry reasons, for manufacturing reasons. But because of our chemistry, because of our unique manufacturing method, we actually could reach meaningful internal resistances so that we could address the LPWAN space. And so there was a really good fit there, and there was a really great way for us to differentiate against the competitive field. I'd like to take credit for having thought of this strategic link between our batteries and LoRa, but actually we only really came to this realization because Semtech already had figured that out, and they actually had a vision of pulling us in as a strategic partner to the LoRa community. And so through Semtech, we actually got to understand LoRa requirements and state-of-the-art of the technology, and from that, we designed a battery specifically for LoRa. And so, we've taken out some of the hard work and the iterations that you might have to go through in the early days. We designed a battery that's credit card shaped. It allows over 1,000 uplinks. So it's in a meaningful form factor, and it's been validated by our partner at Semtech. And because of their partnership, we've actually been able to make this battery in production. So we offer it in developer kits so that you can get your hands on batteries very quickly and do testing. What's really exciting too is we built some reference designs. I'm gonna pull out one of these designs from my pocket here. So this is a LoRa smart tag. It's got our battery. It's thin, flexible, and it works. And the really exciting thing about this is it's a really nice backbone for a lot of these smart label, smart sensor, smart tag applications. This was actually designed for asset tracking. So let's say you're sending a very important package to somebody, and you want to make sure that it gets there at the right location and at the right time. And so the moment that that package is opened, its location and its ID and its time would actually be sent out through LoRa. So this is, really a really interesting use case, but just the starting place for a lot of the applications that we're seeing. So, why I wanted to show this to this community is to let you know that you don't need to start from scratch. There's already a platform to build off of, and there's been some validation that's been done. And so we'd love to talk with you guys at your early stage of design and really accelerate your momentum moving forward. I love talking about technology, but in reality, I'm here to talk about solutions. And so I'm really excited to learn about your dream products, and hopefully we can enable some of the applications that you are creating. Thank you very much, and I'm happy to take any questions.
Thank you so much. Are there any questions at this stage? Yeah. One sec. No, you don't have to push anything. My colleague will do that. Yeah.
Do you have any dev kits with you?
I don't have them with me. I didn't travel with them, but we can ship them out pretty quickly. So just come see me, and I'm happy to arrange for them to be shipped over.
Okay. Check the box, Christine. Very good.
Yeah.
Another question, all the way on the other side. Yeah.
Hi.
Hi.
What is the temperature operation of your
The
bed?
temperature range.
Yeah.
Yeah. So we've tested at this point down to I think -30°C and up to about 65°C. There are impacts. Batteries of all sorts are impacted by temperature. So in colder temperatures, internal resistance goes up. At higher temperatures, internal resistance goes down. So it's balancing that impact with your application.
Okay, thanks.
Do you have an application with very low or high temperatures that you're asking?
Yeah, I have an application with low temperature and a high, so
Okay.
the same.
Then it makes sense to ask that. Yeah, very good.
Yeah,
Great. Another question here. Yeah.
So what's the actual capacity of the battery in milliampere hours? For example, that one that you're holding.
So this is a credit card size pack. There's actually 2 cells in series. So a single cell is 50 milliamp hours. And why we have 2 cells is this system needed 3 volts as a starting point. But bigger battery, bigger capacity, smaller battery, smaller capacity, and that's fairly linear. That's like sort of just like an aerial computation.
Okay, and what's the degradation cycle count? I mean, when it starts to degrade, how many times can you recharge it?
Yeah. So it depends on the methodology of recharge. So like the rate of charge and what voltage windows. So for deep discharges, we're around 300 cycles or so. But for shallow discharges, which are more common for energy harvesting, we've done more than many thousands or so. And so the cumulative capacity, for example, for this battery can be on the order of like hundreds to even thousands of milliamp hours with that type of charging.
That's amazing. Thank you.
Cool. Christine, thank you so much, all the way from San Francisco. A big hand
Thank
for
you.
Christine Ho.